of the copper content in brass using UV visible spectroscopy. So basically in this lab you're going to take a brass object. I have some screws I might be able to give you. I have some 22 gauge rifle shells. You are welcome to bring a brass object from home too if you want to figure out the copper content in that object. You just have 3 requirements if you want to bring a brass object from home. The first requirement is that this object is going to get destroyed. So don't bring something you really care about. 2, it has to be pure brass. So if there's anything in your object that is not pure brass, you can't bring it because we're going to be reacting the brass with nitric acid. And if there are any impurities, we don't know how that's going to react with the nitric acid. So we don't want to have any impurities in our solution. Or sorry, in our solution. The third requirement is that the volume of the object must be less than 5 milliliters because we're going to be dissolving this in nitric acid and putting it in a 50 milliliter volumetric flask. So we just need to make sure that volume is less than 5 milliliters. So small brass object, pure brass that you don't mind getting rid of. If you want to bring that in, that would be great. Otherwise, I will just supply you with brass objects that I have brought in. So we're going to be taking that brass object, we're going to be figuring out the copper content of it using UV visible spectroscopy. UV visible spectroscopy, I know we've thrown this word around a couple times, it's really just another word for colorimetry. So in Greek, scope means to take a look at, so we have microscope, telescope, and spectrum is really just referring to the electromagnetic spectrum. So in chemistry, there are lots of different kinds of spectroscopy. In UV visible spectroscopy is going to focus on the ultraviolet and visible parts of the electromagnetic spectrum. And since another word for the visible portion of the electromagnetic spectrum is color, colorimetry is another word we can use for UV visible spectroscopy. So, in order to determine, the copper content in brass, we're going to follow several steps. So the copper content in brass is going to be expressed primarily as a percent mass of copper in the brass object. Now later in your lab reports, and I'll explain this a little later, you're going to go on to find the mole fraction of copper in brass. Fundamentally, you're going to express this as a percent mass. So remember, percent mass is just equal to the mass of copper divided by the total mass of the object times 100%. All right, so in order to find this percent mass of copper in your brass object, you're going to have to record the mass of the object. And this is very important that we remember to do this before we destroy our object. So the first thing you should do is to record the mass of the object that you're going to be measuring. Okay? And then we got to figure out the mass of copper. Now figuring out the mass of copper is going to be very hard. Because remember, brass is an alloy of copper and zinc. So that means we have our zinc atoms and we have our copper atoms, and they're all kind of mixed together in this hard solid. So we're not going to be able to separate out the copper atoms to measure their mass separately, at least as it exists as a brass object. So what we're going to do instead of measuring the mass of the copper in the brass object, we're going to have to figure out a way of isolating the copper from the zinc. Now the way we're going to do that is using nitric acid, HNO3. So what nitric acid is going to do is it's going to oxidize both the copper and the zinc in the brass sample. So instead of having a copper and zinc atoms very close together, what you're instead going to end up with is copper ions, so with a +2 charge, copper ions, +2, and zinc ions, I'll just draw them as black, +2, floating around in an aqueous solution. Now you may be wondering, Mr. Pell, you haven't isolated the copper from the zinc. You haven't separated the copper from the zinc. The copper and the zinc are still together in the same aqueous solution. But we can exploit something to our advantage. The thing we're going to exploit to our advantage is that the zinc ions do not absorb any visible light. But the copper ions, as we can see by this graph over here, the copper ions absorb light between 500 nanometers and 700 nanometers. In other words, they're going to be absorbing red light. That's why copper solutions appear blue. So zinc does not absorb any visible light. Copper absorbs red light. So if we can determine the absorbance of red light of our dissolved brass object in nitric acid, we can determine the concentration of copper. So we're going to have to determine the concentration of copper. Now just to kind of show you, when we get the concentration of copper, we can multiply by the volume of copper, the volume of the copper solution, to get the moles of copper. Remember, concentration times volume is moles. Because concentration is moles per liter, you just multiply by the number of liters, you're going to get the moles, right? And then, so we get the moles of copper, then we're going to have to multiply by the molar mass of copper to get the grams of copper. Once we have the grams of copper, we can find the percent mass of copper, which is what we were trying to find all the way over in step 1. Okay? So if we know the concentration of copper, we can now find what we were looking for. So the concentration of copper, if we'll remember by Beers' law, is related to the absorbance of the red light by the following equation. Absorbance of the light is equal to the molar absorptivity value times the path length times the concentration. So since we're trying to find the concentration here, we have to record the absorbance of our solution. And we will know, I'll just tell you, the path length is going to be 1 centimeter, and then all we need to find is the molar absorptivity value. So we've got to find the molar absorptivity value, but before I talk to you about how we're going to find that, just remember that in order to turn the concentration of copper into moles of copper, we've also got to know the volume of the copper solution. So in order to find the volume, I'm just going to give you the volume. So what we're going to do, you're originally just going to dissolve your brass object in nitric acid, so you're going to get a very acidic blue solution. Then you're going to pour that into a 50 milliliter volumetric flask and fill to the line with water. So that way you just know that the solution you measure the absorbance of is 50 milliliters. So, and when you use the volumetric flask, you know that to 4 sig figs. So the volume is just going to be 50.00 milliliters, provided you do that all correctly. So we have our volume. We're going to record our absorbance. And then the only thing left that we haven't been able to figure out, that we need to figure out in order to find the percent mass of copper, is that molar absorptivity value. In order to find the molar absorptivity value for copper nitrate, we're going to have to do a serial dilution, which many of you have been able to do in class already. But basically, you're going to take a solution. You're going to take a solution of copper nitrate of known concentration, known molarity. So you're going to have to record the molarity. It'll be on the label. But I haven't mixed the solution yet, so I don't know the molarity. And you're going to put 10 mils of that into one test tube, and then 8 mils into the second, 6 mils into the third test tube, 4 mils into the fourth, and 2 mils into the fifth test tube. And then you're going to dilute to the line with water. So then you're going to add 2 mils of H2O to this, then you're going to add 4 mils of H2O to this, 6 mils of H2O to this, 8 mils of H2O to this. So you have copper solution, and you have H2O that you'll be adding. Now, you're going to be able to record these volumes to the nearest hundredth using the volumetric pipettes. So you will not have exactly 10.00 mils. You will not have exactly 8.00 mils. So you're going to have to make a table and record the precise volumes that you use. Then using your dilution equation, which if you'll remember from Chem 1 is M1V1 equals M2V2, you're going to be able to find the concentrations of each solution. Then you're going to have to record the absorbance values of red light for each solution. What you're going to do with that information is you're going to make a graph. The graph, you're going to plot the concentration on the x-axis, the absorbance on the y-axis. And because Beers' law holds, absorbance equals path length times molar absorptivity times concentration, assuming this is a line that goes through the origin, which hopefully it will be, the slope of this line is equal to the molar absorptivity times the path length. We know that the path length is 1 centimeter, so by recording the slope of the line, we will be able to find the molar absorptivity, which will then allow us to find the concentration of our unknown solution, which will then allow us to find the number of moles of copper in our unknown solution, which will then allow us to find the mass of copper, which will finally allow us to find the percent mass of copper. So, we're going to go, again, from molar absorptivity to concentration, to moles of copper, to mass of copper, to percent mass, which is what we're looking for. So, as you can probably tell, this is a lot more complicated than any lab you have done in Honors Chem. So we will be going through this again in class, but I wanted to get you some sense of the lay of the land, some sense of what you had to do. Definitely, I want you to understand all the different things you're going to have to record, because in class, next time I see you, we're going to be talking about writing a procedure based around the things you have to record. So make a note of all the things you have to record, make a note of the processes you're going to use for that, and I will see you next class.